Mathematical modeling can be used to better understand and predict tumor growth. Here, we consider two populations of tumor cells classified by their sensitivity to radiotherapy: those that are resistant to it, the resistant cells, and those susceptible to it, the control cells. We use competitive Lotka-Volterra equations to model the rate of volume growth of both control and resistant cells. The rate of birth of each type of cells depends on the volume of both types of cells. The growth of cells cannot exceed a maximum or carrying capacity of the environment, and competition exists between the cells. Bayesian inference consists in updating a prior belief you hold by using data. Bayesian inference uses Bayes' theorem to update a prior distribution of possible parameter values to a new posterior distribution. The multiplication of your prior belief by the likelihood of your prior belief given particular data is proportional to your posterior belief. Mathematically, the prior is the probability P of parameter values, theta, the likelihood is the likelihood L of theta given data, and the posterior is the probability of theta given data. We said that the posterior is only proportional to the likelihood times the prior, but that's because we didn't show the denominator, which is just a constant number. If we include it, we get the following formula shown below.
So to do Bayesian inference on the parameters of our model, we decided to first test the methods by simulating our model with some test parameters to generate fake data, from which we should be able to extract the parameters back up to some uncertainty. We first tried to extract an estimate of the parameters using the simplest method, maximum likelihood. We only look for the most likely parameter using a uniform prior. MATLAB lets us do this, and we indeed recover reasonable looking parameters.
Approximate Bayesian computation, or ABC, is a method that allows us to find a distribution of probable parameters instead of the point estimates that you can get from maximum likelihood. These distributions of probable parameters are the unnormalized posterior distributions, which are the numerators of Bayes' theorem. But how did we get them? Each parameter is sampled from a prior distribution that we chose to be normal or Cauchy. Then the Lotka-Volterra system of ordinary differential equations is solved using these sampled parameter values. The solution is then compared to the data we're trying to fit, and if it's close enough, the parameters that were used to generate that solution are accepted. This step exempts us from using a likelihood function, which can be costly to evaluate. On the left, you can see the rejected solutions. They are rejected because they are too far from the true values. On the right, you can see the ones that are accepted. They look much better. We plotted the accepted solutions of the ABC algorithm as violin plots to see whether the algorithm was behaving correctly. On the top right-hand corner, the values simulated for the sum of VC and VR are shown. At the bottom, the values for VC are shown on the left, and the values for VR are shown on the right.
The Metropolis-Hastings algorithm attempts to approach exact Bayesian inference by sampling parameters using a Markov chain, which is like a generalized random walk. This is thus called a Markov chain Monte Carlo method, or MCMC. The idea is that if you choose the probability of taking a step right, after a long time you will be sampling from the posterior distribution, and it only requires knowledge of an unnormalized posterior, that is, the numerator in Bayes' theorem. Here we can see the random walker, or Markov chainer, testing the waters before deciding to take a next step for a particular parameter in our model. The red dots show the proposals, and the green dot the accepted step. We can show the trajectory of the walker on the space of two parameters. We can at the same time compute the marginal histograms from the sampled points. These are approximations to the marginal posteriors. In here we can see that these two particular parameters show correlation in the posterior. From the posteriors we can get point estimates like the posterior means, but we can also use the whole posterior distribution to build a predictive posterior, and see that, thankfully, our model predicts things that look like the real data. We also use the Hamiltonian Monte Carlo method, where you're not only clever in how you accept your steps, but you're also clever in how you take them. This method performed the best, and so we'll use it to compare different models. We can see that the model is able to replicate the data it was trained on. But what we really care is if the model is able to predict things we don't yet know. To simulate that, we use leave one out cross-validation, where we divide the dataset in 5 chunks train on 4 of them and test how well our model does on the one we haven't trained on. And it does quite well. We can also show histograms of the log likelihood of the test data after sampling a set of model parameters from the posterior. The higher the likelihood, the more likely it is that our model would have predicted what we have observed. These numbers are not really interpretable on their own, but it allows us to test between models. So we tried a similar but different model, comparison growth, and it shows a bit more mass towards higher likelihood. This simple cross-validation that we did has a disadvantage. We have trained our models on less data, and so they will have to be worse. An alternative is to use something called information criteria, where you can test on the same data you trained with, as long as you compensate somehow for overfitting. Approximate leave-one-out cross-validation does this, and it also shows that the comparison model is probably better.